Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so I'd like to take this opportunity to tell you a bit about what we've been doing recently on modeling 3D surfaces from single images, something we've been doing for a while now. And before David Forsyth asked me why I do this, I'll try to answer preemptively, which is, of course, you could say, why bother? This is the home of the Kinect. Who needs monocular modeling of surfaces with a single camera? And the answer is, well, there are still cases where it's hard to use a Kinect. And also, where we want to go in the end is we want to do this on a mobile device. So it's not clear that you will have this kind of a sensor in mobile devices anytime soon. So first, I would like to present what we had done so far, and then go on to how we've extended it recently. So the kind of problem we've addressed for a while is, let us say I have a deformable surface. I have one image, which I'm going to call the reference image, in which I actually know the shape. So in this case, it's flat. It doesn't have to be, but in this specific, it is. And so this is essentially a template. And now I'm given a second image, which I'm going to call the input image, in which the surface is deformed, and I want to recover the 3D shape. So of course, this is not stereo because the shape is different between the two images. So the way that we formulate the problem is as follows. We have our reference shape. We know where it projects in the reference image, and we establish correspondences between the reference image and the input image. And what we're going to try to compute is our unknown, x, which are the 3D coordinates of all the vertices in the mesh. And what Mathieu Salzman, who used to be one of my students and now is a researcher in Australia, showed is that you can do a kind of a DLT and formulate this as a simple linear problem where x must be the solution of an equation of the form mx equals 0 if x is expressed in the camera coordinate system. So you could say, well, it's easy. Just solve that. Done. The problem, it's not quite so easy because the M matrix is very ill-conditioned. In fact, if you do an SVD, 1/3 of its singular values are 0 or almost 0, having to do essentially with the depth uncertainty. And so you can't just solve. You have to impose additional constraints. And what Mathieu did in his thesis is try essentially many ways of imposing constraints, and in the end, the conclusion was one of the best ways was to enforce inextensibility constraint in the form of inequality constraint, saying the distance between individual vertices cannot be greater than the geodesic distance. And with one little twist is that if you only impose this kind of constraint, nothing prevents your mesh, the one you're trying to reconstruct, to shrink to nothing. So you have to add something that's akin to balloon forces that pushes the mesh as far as possible away from the camera until as many of the inequality constraints become essentially equalities. And what he showed is that this, in fact, is a convex problem. It's an SOCP, so you can minimize and find a global optimum and generate results like those. The final result is bottom right. So you have, well, Mathieu's manly chest and the reconstruction in the lower right. And what's important is this is really done one frame at a time. We're not tracking We are reconstructing in every frame individually, and it's pretty stable. So it works nicely, but it has one problem, is that we are solving this SOCP. It's convex, that's nice, but it has lots of variables. Because we have a mesh that's about 40 by 30, that's 1,200 vertices times 3,600 variables, that's a lot. It doesn't run fast. It's nowhere near real time. So one thing we have looked at since is how can you reduce the number of variables so that you solve the problem with far fewer variables, and that's actually work we did with Raquel and Mathieu again. And one observation is you could train a system to reproduce these inextensible. So we are limiting ourselves to the case of inextensible surfaces. And one way to reduce the number of variables would be to come up with a latent variable model in terms of far fewer variables than the 3,600 I've talked about that would parameterize the space of inextensible surfaces. So the simplest thing you could do, and we've played with this, is to do PCA. It is a latent variable model. Unfortunately, it doesn't preserve length. So when you add deformation modes, length between vertices are not preserved. Another thing we tried is, well, you could actually learn a Gaussian process, and then we have the influence of this harkens back actually to things we did with Raquel, David, and Aaron on body tracking. So actually it is a good example of the interaction between graphics and vision. Same algorithm. I think this whole thing started as a graphics animation kind of thing. And you could learn a Gaussian process by essentially given examples of deformed mesh, and you could learn, for example, a GPLVM that would have fewer parameters. The problem with this, and the reason it was not completely satisfactory, is to make it work well and to make it preserve length for all possible values of the variables, you need a huge training database, and large enough that it's actually not practical. So that's the work we did more recently. So first, let's start with the simple thing, which is, let's just say X are going to be my latent variables, the Y's are going to be the meshes I'm trying to reconstruct. I could imagine having a database of these things and learning a mapping, a nonlinear mapping in this way. So this is the primal problem would be something like this with a quadratic loss and a quadratic regularization. And if I kernelize all this, I get a GP that would essentially produce meshes whose lengths are preserved if they are near the training samples, but not if they're far away. So the little twist that we added was to say, okay, what we are going to do is we are going to have the same training database for which we have both a set of latent variables and a mesh. We are going to minimize essentially the same loss function, but we are going to introduce other latent variables for which we don't have the Y, and we are going to impose that for those, the mapping preserves the length. And so what's interesting about this is you can, if you work out the math, you get actually something that's fairly similar to a GP, and you get a nonlinear mapping that actually preserves better the length over the whole latent space.
So what are these latent variables?
They are the X. So you start, for example, from the weights of the PCAs. Like, it's the same way when you compute a GPLVM, you start with the weights of the PCA and then you do an optimization. And you do exactly the same thing in this case.
So in this case, there are less artificial latent variables, but this is regression, right? So it could be also training necessity.
And so what that does is you can see the, so I should run it back. what you can see is the reconstruction using three possible methods we've played with. Either you do it with PCA, or you do it with the unconstrained GP, or you do it with a constrained GP. And you get better accuracy, it's better trained when we impose this constraint during the training. Here's another example along the same lines, where these graphs are the errors frame by frame. And you can see, generally speaking, the red curve is below the others. So this is a way of learning a model that essentially enforces the constraints. So it's a mapping, nonlinear mapping, that whose output really tries to satisfy the constraints, even for values of latent variables for which you don't have a corresponding y. Yes?
So, as I understand, you have this grid. You have the position of the grid vertices in image space.
Yes.
But then to derive the deformation is an ill-posed problem, because there are several solutions, obviously, for the same input. So how do you deal with this?
Fundamentally, it is the inextensibility constraints that make it well posed. So if you don't impose that the distance between vertices is bounded, then you have an infinity of solution. If you now try to preserve it, you have one solution that preserves it better than the others.
So you're saying there's always a unique solution?
I'm not sure. I can't prove it. But in practice, yes.
During learning, do you see some problems with local minima?
No, because it's a convex. Is it convex? No, it's not. It's not convex. But it's essentially, I think, what makes it work is that we start close enough so that we do get convergence with this. And what's interesting about this is I have formulated this in terms of learning a mapping that preserves distances between vertices. But, I mean, this is a complete generic formulation. So this idea of these constrained LVMs is actually, I believe, applicable to other problems if you so choose. Okay. Any more questions on this?
So instead of imposing constraints on the weights, which may or may not satisfy them for new predictions,
right,
you can also try to impose them at time of inference. So you learn the predictor and then project, when you do inference,
right,
project onto this constraint.
Which is essentially what we used to do. Because in the previous method we did this, the potential advantage of this is we have far fewer variables to deal with because we don't do the projection. We are directly in the latent space.
Then are you guaranteeing that you're actually going to satisfy the constraints in the end?
No, we guarantee that we are close. We don't satisfy them strictly. But we've tried, and I mean, on many examples we run, empirically they are close to being satisfied.
It's more of the speed, right? It's a nasty optimization problem, right? You have a lot of inequality constraints. And if you do that at inference, it takes for a long time. If you impose the latent variable, then you can get much faster convergence. Even if you impose it.
Another question. There's nowhere in your very generic formulation that says it has to be a rectangular piece of surface. So actually you could do it on quite different topologies as well.
Right. I mean, it's
deformable, Teddy, I don't know.
We've played, I don't have the results here, but we've played, for example, with the human EVA data sets, where the kind of things we impose is that the distance between joints are preserved. And it's no, I mean, the mathematics are the same.
Exactly, that was my question. And if you put it all together, so you just scramble it to a ball, then obviously it's really difficult to find out the shape. What happens with extreme deformation? deformation extreme occlusions.
So,
What are the limits?
what are the limits? It's probably, it would have to do with the size of latent space. Essentially, the size of the latent space is going to control how much you can deform your surface.
Which means that you need more training samples.
Yeah, if you want to really sharp folds, you're going to need more training samples. Yes.
So have your results, which I don't know, I talked to Andrew Fitzgibbon like last week about it. He kind of says like you always see these kind of papers move around or some shirt, but I mean really deformable surfaces like a dog running or sorts of things. I mean it's like quite or more deformations, right? So yeah, is that a challenge or is it like?
Of course it's a challenge, and that's exactly what I try to tell my grad students. We've seen enough paper. And we should see different things, and hopefully we will see them. But we've been moving, if you look at some of the recent papers, we really have made an effort to go towards things that crease sharply and can get somewhere in that direction. But of course, it becomes increasingly difficult.
Yeah.
Not least because when it creases sharply, you don't have the correspondences anymore.
No, I'm not saying it's not. It's very challenging.
No, I understand. I completely agree. I completely agree.
And how far do inaccurate observations do the problem for the optimization?
Not that much, because there is a robust scheme to eliminate outliers. So you do an iterative thing, you do the first fit, get rid of the outliers, and fit again.
So you handle them explicitly?
I'm sorry?
You handle them explicitly by checking for them?
Right, yes. But municipality, it's a completely standard outlier rejection scheme.
Two somewhat related questions. One is just what do you use to establish the correspondences, and how does that relate to how you think the
I'm sorry, I didn't. Can you speak louder, please?
What do you use to establish the correspondences between frames, and then how does that relate to the resolution of the mesh that you pick?
Okay, so actually, give me a moment, because that's my next comment is, of course, you've all noticed the examples I've shown you were very textured. There's a good reason for that, because where there is no texture, I don't have any information. So actually, thank you for providing me my transition. That's the next problem on the list. What do you do with surfaces that are not very textured? And there you essentially try to revisit shape from shading. So here is our version of revisiting shape from shading in the light of what we know about learning these days. So here's an example of, so Aideen, who's a grad student who did a lot of this work, is here. He's still holding a piece of paper. But you may notice that this piece of paper that he's holding doesn't have that much texture on it. So it has a bit of texture in the center, and not that much on the side. Plus, he's actually in his office where the lighting is not a simple point light source, it's whatever it is. There's this big window on the right side. It's an extended light source. That's what you have to deal with if you want to do shape from shading. So how do we handle this? What we're going to do is we are actually going to calibrate the lighting. So initially we thought we were going to learn the lighting as well, and that proved, for the time being, that proved too difficult. We weren't able to do it, so we stuck a light probe in the environment and learned a mapping model in terms of spherical harmonics, which for this environment actually seems to be enough. And then what we wanted to do is, given this lighting model, and given the image of the sheet of paper that we have, what can we say about this shape? So without essentially, it's shape from shading, but without some of the simplifying assumptions. And what we try to do is to say, well, we can learn a mapping between deformations and intensity patterns. So for individual patches on the surface, what we did is to actually compute deformation modes. This time, this was done strictly in terms of PCA. It could actually be done in terms of what I just presented. But since we did this actually before the other, that was done in terms of PCA deformation modes. And to each of these things, what we computed were given a shading model for a particular shape of a patch, we can predict what the intensity is supposed to look like. And we can also do a PCA style decomposition, which means we can associate a set of intensity modes to a set of deformation modes. And again, we learn the GP between one and the other. So that when we see a little patch on the surface, we can actually predict what shape it might be. So
intensity is the shading, basically.
It is the shading.
It's white paper.
Right. So it's albedo is constant.
Yeah. Okay.
And it is the shading. But it's a slightly more generic form of shading. So it's easy to say. One of the problems is it doesn't quite work this way because it's actually, you cannot learn one mapping this way because you can have several shapes that produce the same intensity pattern. And the way around that is to say it's true, there is not a one-to-one mapping if you don't say anything about the average normal of the patch. But if you partition the space, the training database, according to the average normal of the patch, then for each average orientation, you do get a pretty good mapping. So, which means that, so that's how we train. We essentially learn several GPs, one for every single average orientation. And then at runtime, when we see a patch, we predict several possible shapes according to the normal. So we associate several hypotheses to every little patch. And then when we do the reconstruction, what we do is for every patch we got a bunch of hypotheses and we run a Markov random field to find those that are globally consistent. And that's actually why there is a texture patch in the middle. That's what's needed to make it work, which is essentially that gives us boundary conditions. It gives one patch for which we actually can compute the shape using the previous technique. And by then enforcing consistency on everything else, we get the complete shape, which is what you see on the right on these papers and T-shirts.
Question, could you actually also use the silhouette as a boundary condition?
Yes, definitely. I mean, that's, it's obvious that one of the things we are missing are the silhouettes that we should definitely use. Yes?
The patches that you use, they're all available geometries at a particular scale, or they're selected from example objects?
We've trained for this particular kind of object, so they are, how should I say that? They are for one specific scale. And I guess I didn't quite understand your question, maybe.
The reason I'm asking it is can I think about this as a non-parametric representation of a geometric prior on the surface?
Right.
Some patches are available to me, some are not.
Right.
Is that?
Yes, that's what it is.
So then maybe we're also looking at some very, very recent stuff by John Barron and Deformable on shape and shading, where they essentially argue that the surface prior is everything, and that if you use it right, you can duck using boundary condition.
But actually, we are not using boundary condition in this case. What I was answering is, sure, it would be, I mean, it probably would constrain the thing a lot more, but in this specific case, we weren't using them really, except for the textured patch.
So that's a weighty difference between what you're doing in conventional shape and shape. Both you and Barron and Malik are essentially arguing that the surface prior sort the details are.
Yeah.
You which I think is cool. It's a neat argument. And it's a very new way of looking at things, or a very different way of looking at things from the tradition.
The training is done assuming a Lambertian reflectance model?
No, well, it's using basically the spherical harmonics model and the diffuse model, yes. Right. So, again, it's kind of...
But the paper here is somewhat specular. So you still have to, you have your illumination model and then you assume the reflectance of the patches is Lambertian.
Yeah, it's Lambertian, and for the time being, it's... So basically what you're assuming is constant albedo in every single patch. It doesn't have to be the same patch to patch, but within a patch, it's constant.
So this argument about priors gets exciting because Barron and Malik argue that you don't need constant albedo because you can just use albedo priors and it'll all come right. And it's not beyond the wit of man to say we could use priors on illumination as well. Now, they don't actually do that, but you can sort of see it happening.
But if the illumination weren't as complex as you have here, there'd be no reason to learn this.
No, it's
Because it's easy to, if you have point light sources.
Sure, sure. So this was an attempt at getting away from the point light source model.
I disagree with Mike. I think the reason to learn it is because the surface prior sorts it out.
Really, you just learn the surface prior, the relationship between the surface shape and what you actually observe.
No,
Light source is simple.
Yeah. It's the product thing. Yeah. But there's a change, right? If you track this into shape from shading circa about 2 years ago, it wouldn't make it. I mean, that's...
Okay, so to be honest, so the conclusion of this, I mean, I wouldn't sell this as the solution to shape from shading quite yet. Our observation is this works nicely provided you calibrate your camera well, photometrically. And that was what Aideen's experience was with this technique, which is until he did the radiometric calibration of the camera correctly, it wasn't working. When he did it, it started working correctly. So means it's not really the answer to the universe, but it's hopefully an interesting step forward.
So just to clarify the comment about surface priors and things like that, I mean, you were the first person when you were at SRI, I think, to have a parametric model of shape and shading. You had a model of face shape or maybe something else, I forget, landscape.
Right.
And related the appearance to the surface jump. So that actually is a very good idea. And it's more general than what you're showing here.
But so at the time, the old SRI stuff was still a point light source with the usual assumptions because I had never heard of statistical learning at that time. Okay, so here are some results where we compare what we get. So we are not complete Luddites. We do use Kinects once in a while, just if only to produce the ground truth. And where we can show that, at least on these examples, we get some reasonable reconstructions. And of course, they are better than the one we obtained using the previous technique because we chose our examples right. There is not enough correspondences on this piece of paper to do the correspondence only thing. And that gives you maybe also, so here's another example of what we can do. And one way we actually validate this is this particular implementation actually does not enforce the geodesic constraint. It does not enforce the length constraints. So it's actually a good way to measure, to find out if the result we get is reasonable. And so we've checked that when the reconstructions we get, these distances are actually preserved on something that we know to be inextensible. Okay, so to conclude, it's what the direction we are going in slowly, but hopefully in the right direction, is essentially a generic paradigm where you have a method whereby with a simple webcam, essentially, you can reconstruct the textured part of the surface using correspondences. You can reconstruct the constant albedo parts using the method I've just shown you, the shape from shading style technique. you can use these two things to learn a model of the deformations and then use that to reconstruct the rest of the surface that you couldn't handle well without a good deformation model. And so the end, I mean, we're still going to be working on this for a while, and I promise that we will try to show other things than paper and T-shirts, is something that would be generally applicable, that one of these days will run on the phone, and it doesn't yet, but if you, at CVPR, we'll have a demo, so we will be happy to show you that it actually works for real, in real time, on a laptop. Thank you.